Hello, everyone, and thank you for joining in another Shimadzu webinar. My name is Donald Stahl from Shimadzu's Materials Testing Division, and I will be your host for today. For today's topic, we will be discussing common standards for mechanical testing of composites. Before we start, I would like to introduce you to the webinar's features and windows. Starting on the left side of your screen, you will notice the slides window where you can view today's presentation. Directly below that are resource links that will navigate you to additional resources related to today's topic. In the center of the screen is the Q&A window. Please submit questions through the Q&A window at any time during the presentation. We will try to answer all your questions during or after the webinar. However, if we did not get to your questions today, we will follow up with an email. On the right side of your screen, you should see a set of survey questions. Please take a moment to answer these survey questions at any point during or after the webinar. Your responses are truly appreciated and they help us tremendously. Finally, at the bottom of your screen are icons which can restore these windows in the event they are closed or minimized during the presentation. It is now my pleasure to introduce our presenter for today, Dr. William Gabler. William is a senior application scientist in the materials science group at Shimadzu Scientific Instruments. He joined the company after obtaining his PhD from North Carolina State University, where he researched mechanical and chemical test methods for polymers and textile products. At Shimadzu, he is responsible for supporting sales, applications, training customers, and researching new applications. He helps support mechanical testing, fatigue, thermal, particle size, hardness, rheometry, and X-ray instruments. So without further ado, I'll hand the reins over to William. William, what do you got for us today?
Thank you, Donald, for that introduction. So today I'll be discussing some common composites test standards, and I won't be going into kind of every detail of each standard, but rather tried to give an overview of the general categories of composites test standards, the reasons they are used, and kind of some general guidelines on things to watch out for as you may prepare to perform these types of tests. First, the term composites can be broadly applied to any type of material composed of two or more distinct phases of materials that, when combined together, give unique characteristics. This broad definition would include many different materials, some naturally occurring, such as wood, and other materials that have been used industrially for decades, such as reinforced concrete, particle board, reinforced plastics, and many others. In this presentation, though, I'll be focusing on the class of modern advanced composite materials, which are most commonly used in aerospace, automotive, and industrial manufacturing, and kind of what people generally refer to when they use the term composites generically, and that's going to be long fiber reinforced composites. These consist of a matrix of material that is reinforced with long aligned fibers. The fibrous reinforcements are strong and stiff in the fiber direction, but otherwise pliable and weak in the transverse direction. But when bound in the supportive polymer matrix, the applied loads are shared between the fiber and matrix to create strong, lightweight materials. The fibers can be made of glass, carbon, different polymers, mineral fibers, and even natural fibers, and they can be incorporated in the form of yarns, fabrics, and chopped strands. And the matrix is typically a polymer, such as an epoxy thermoset or maybe a thermoplastic. And the matrix, though, can also be formed of metal, ceramic, carbon, and other materials. So these composites are referred to as laminate composites because they're made up of a series of stacked layers or lamina. And each layer is going to consist of some layer of fiber reinforcement along with polymer matrix. That fiber reinforcement can either be a series of yarns, which are twisted bundles of individual fibers, tow, which are aligned bundles of fibers, or it can be a fabric, such as a woven fabric, which is made of crisscrossing series of yarns or tow, or even a tape, which is simply a narrow, flat section of fibers. Each of those fibers, along with reinforcement, is referred to as a ply. And a central concept of composites is that the strength of a composite will be strongest in force that's aligned axially to the direction of the yarns and fibers. That means that the strength is going to the strength of the composite is going to depend on whether it's applied axially to the fibers or not. So, when regards to referencing fiber composite testing, we often reference the orientation of the plies. And the orientation is the angle between the ply principal axis and a reference direction. And the 0-degree principal axis is usually displayed horizontally and is going to be typically the long axis of the part. And then we can refer to other plies as they're oriented within the material in reference to that 0 degrees, such as 45 degrees, 90 degrees, which would be perpendicular, and negative 45 degrees. A few terms about how these types of composites are constructed. They are typically made using tooling, which are molds used to form a part. So you create first a mold in the shape of the composite material you want, and then you lay the series of plies onto that mold. And this process is called layup. That layup process can be performed in many different ways. One such way is using pre-preg, which are pre-prepared yarn, tow, or fabric that is impregnated with resin and can later be cured, such as by heat in an autoclave. There are also several other processes, such as winding, which is the process of wrapping yarn, tow, or tape to form a part, typically in some sort of automated machine. And this would be typical, as you can imagine, for cylindrical or symmetrical parts. There are also methods such as resin transfer molding, where the tapes or wovens are laid up onto a form, and then at a later time, the resin is infused with pressure or with vacuum. And then there are also thermoformed laminate composites, which is the process of forming a thermoplastic composite where the resin can be cured or formed by applying heat and pressing the composite into a form. An example of that is with sheet molding compound. So now taking a look inside the layers of a theoretical laminate composite, there are many different stresses and potential failure modes that can happen within the composite layers. And these include delamination, which is the separation between layers, fracture within the matrix due to either weakness from the polymer matrix or from voids and defects, as well as fiber pullout and debonding, which is going to be a failure at the fiber matrix interface, and then also fracture of the fiber itself. And you'll see through the series of the test methods that I review, the wide variety of composite test methods are basically designed to analyze the different potential failure modes and characterize them depending on how the fiber matrix composite is constructed. A few other terms that are commonly going to be used in these methods. One is the term interlaminar, which refers to forces applied between the layers, and it also specifically is applied to shear stresses applied perpendicular to the plane of the ply, so through the thickness of the laminate. Another term, complementary term, is in plane, which would be parallel to the planes of the ply or within the ply. And we also will refer to axial forces, which are either can mean applied along the fiber direction or just along the length of the part. and then transverse forces, which are going to be perpendicular to the axial force. And there's a common diagram, too, that's used across many of these ASTM standards, which is depicted in the bottom right, which basically defines a composite, a model of a composite laminate in terms of each of the three directions that you can orient the composite. So the primary axis being in line with the fiber direction, the secondary axis, which is transverse to that, and then the third z-axis, which is through the laminate direction, so through the thickness. And many of the test standards refer to this material coordinate system to define the stresses that are being applied in a test. And just briefly, you can kind of ask, why would you want to test mechanical properties of fibers? Well, of course, there's many different reasons for testing purposes. Obviously, within any industry, there's reliability and quality control testing to apply to screen materials and production operations. There's also interest in research and development, and also the use of these test methods towards modeling research, which are all going to be considering kind of the combination of parameters of what the fiber matrix combination is, what the fiber orientation is, process variables such as how the layup was performed, the temperature, pressure, and different additives used in their environment, and then also how the composite material is going to change in strength in regards to changes in temperature, humidity, and environmental condition. So because of the complexity of composite materials and the variety of their constructions, there have been dozens of different test methods that have been developed to characterize the mechanical properties of composites. And so I'll go over in a little bit of detail each of these general categories, which are really, to summarize, four main categories, which are tensile tests, flexural tests, compression tests, and shear tests. And then a wide variety of kind of specialized tests that can characterize other different mechanical properties. The primary tensile test method for laminate composites is the ASTM D3039 for tensile properties of polymer matrix composites. There are a few other very common standards, EN 2561, EN 2597, and ISO 527-4 and -5 that also provide similar guidelines. The standard uses a rectangular flat or tabbed specimens. This is in contrast to common polymer tensile tests which use dog bone specimens. These aren't really appropriate for composite materials, one, because of the difficulty of preparing a dog bone, and also the stress concentration around the corners just acts differently because of potentially from laminate effects. So it's common to tab specimens in order to reinforce the specimen ends in order to avoid damaging the ends of the specimens from excessive gripping force. And another important factor in composites testing of flat specimens is that the sample width may affect the results because depending on the orientation of the laminates and plies, you may get different effective strengths based off of how the oriented laminates interact with each other. The common measurements for a tensile test are ultimate strength and strain, elastic modulus, and Poisson's ratio. It's common to use an averaging biaxial extensometer, one, because of the stiffness and rigidity of composites. You want to ensure that you are not introducing any bending forces into the sample, because bending forces due to the anisotropic nature of composites can cause premature failure. And if you're performing Poisson's ratio, of course, you would also use a transverse extensometer. And the key takeaway about tensile test of composites is that the alignment of the two grips is very important, again, in relation to the bending forces, which can introduce weaknesses in the result. I'll discuss modes of addressing alignment in the last few slides of this presentation. Two other common tensile tests for fibers is ASTM D4018, which is testing the properties of continuous filament carbon and fiber tows. So you're able to test impregnated resin tow by itself instead of entire laminates, as well as ISO 11566, which is the determination of the tensile property of a single filament specimen if you want to perform tests on a single fiber, which is represented on the right, where it's common to mount a single fiber, since it's very delicate, first into a adhesive or paper mount, and then cut the ends of the mount in order to perform a tensile test. Next, I'll discuss compressive test methods for composites. There are a few different fixtures that are used for compression, and the main issue that they all try to address is to ensure that failure is not caused by buckling. So whenever you're trying to compress a very stiff, unsupported bar, you can imagine that it's possible that bending and buckling forces can be applied. So the first one is ASTM D695, which is actually a plastics standard that has been adopted and modified unofficially for in-plane compression of composites. The fixture consists of kind of an H-bar fixture seen on the right to test a bar-shaped specimen. The supports guide the specimen to prevent buckling. Sometimes there's a central groove to fit strain gauges to measure modulus, and you can use a flat or tabbed specimen. But even though it's mounted in the sample, the ends of the sample actually protrude, so you're applying compression directly to the end of the sample, so it's called an end loading method. The general approach with compression is that if buckling or some other failure mode occurs instead of pure compression failure, such as end failure, tab failure, slippage, or if you see a large amount of variability, then you must try adjusting the method that you're using to perform compression testing or adjust the sample dimensions, such as increasing the thickness or decreasing the gauge length of the sample. An alternative to end loading is a shear loading method, such as ASTM D3410, where this is also called the IITRI jig. As you can see on the right, the sample, either tabbed or flat, is clamped on either end through two tapered grips and then mounted either in a cylindrical guide or a rectangular guide. And here, so the compressive force is actually applied to the guides and transferred to the actual material through shear forces. This can be used to measure compressive strength and strain, modulus, and Poisson's ratio, and it requires a strain gauged sample as well. The downside of this is that it's a rather large, kind of a bulky jig to perform testing. So a combination of the two approaches can be found in ASTM D6641, combined loading compression, or CLC jig. This typically uses an untabbed sample clamped between plates, and the end of the sample is flush with the end of the compression plate. So it's a combination of shear and end loading. The fixture has guide rails, so it's got extremely high alignment. It's got an adjustable gauge length, so you've got some flexibility in terms of what sample size is used. And again, typically requires strain gauges on both sides of the sample to measure bending and ensure that you're applying shear or pure compressive forces. There are a few variations on the compression test and tensile test. The first is open and filled hole testing. So composite strength can significantly decrease around holes and edges and around fixtures and bonded areas due to localized stresses. So a few test methods have been developed to address that, and these are ASTM D6484 for open hole compression, D5766 for open hole tension, and D6642 for filled hole tension and compression. You can see there typically a hole is applied to a composite rectangle, and that bar is then mounted into a jig that can either apply a tensile or compressive force. Most of these don't require strain measurement. They're just kind of comparing the difference between a solid sample and a sample with a hole, but you can perform strain measurement using techniques such as digital image correlation. Another variation is a compression after impact test, which can be found in ASTM D790 and D7137. These are based originally off of a Boeing test method, and there's also a ISO method. And the idea here is that a sample rectangular coupon is damaged in a impact test, such as a drop weight test, and then compressed in a guided form, and compressive strength of the impacted and unimpacted samples are compared. Next are flexural tests. Of course, flexural tests impose a combination of tensile compression and shear tests on a plastic. There aren't many methods dedicated purely to bending tests of composites, but they are still useful because they can show different failure modes of composites. So the two most common flexure tests are D790, which is a 3-point bend test, which applies to both unreinforced and reinforced plastics, and D6272, which is a 4-point bend test. The 4-point bend test applies the axial stress on the outer surface is more evenly applied between the two loading noses, so it can give different results than a 3-point test. Next, I'll review several shear tests. The first shear test is actually a bending test, ASTM D2344, which is a short beam shear test, and similar to EN 2563 and ISO 14130. It's also called the apparent interlaminar shear strength test because of this very small span short beam test tends to cause interlaminar cracks between the layers. It's very commonly used in industry because it uses a relatively small sample size, thickness less than 6 millimeters, and a simple setup. Next are two in-plane shear tests. The first is ASTM D3518 in-plane shear tensile test of a 45-degree laminate. According to, this is similar to ISO 14129. The idea of this test is that if you apply a tensile force to a laminate that has two laminate that are oriented at 90 degrees to each other, and you apply the loading direction at a 45-degree angle, that actually applies a shear force in the plane of the composite. Again, as a reminder, there's the plane diagram for material coordinate systems for composites on the right. And this typically requires biaxial strain measurement and is going to be laminated or limited to composites that can be prepared in this form. Another is D4255, 2-rail and 3-rail in-plane shear test. This test can provide shear strain versus shear stress, shear chord modulus calculations, and in-plane shear measurements up to 5%. It uses a relatively large sample that's mounted between two rails, and the rails are oriented at an angle to each other. And then by applying a tensile force to the two rails, you're going to be applying a shear strain across the planes of the composites. Next are two V-notch shear tests, which can be used for either in-plane or interlaminar shear. D7078 is a V-notch rail shear where a specimen with two V-notches is clamped between two rails and pulled, the two rails are pulled apart. The advantage of this configuration is that there's no edge compression and a greater shear load can be applied. Next is the D5379, also called the Iosepescu test after a Romanian scientist that created the method in the 60s. It, in the case of an interlaminar shear test, has zero bending shear, so it's capable of true interlaminar interfacial shear stress. As a reminder, that's shear stress applied through the thickness. So if you're looking at that sample at the bottom, you imagine that you'd be looking at the side of the plies to perform that test. So it's very common because of the high shear stress that it forms in that central plane between the two V's. For both of these methods, you typically apply two strain gauges at 45 degrees to each other, but they can also be used in conjunction with digital image correlation for video imaging strain. So I don't have time to go into every single composites test standard that's out there because there are many, many more, but to give an idea of a few other common tests, I'll mention for laminate composites, so another common test is D3528, which is the strength properties of a double lap shear adhesive joint by tension. So you can imagine adhering the face of two different laminates together and then measuring the force to pull them apart. There are also tests such as D5961, which is a bearing response of a polymer matrix composite laminate, where there's a few different configurations where composites can be bonded together with fasteners and then tested. Of course, there's also fracture toughness tests, notably D5928, which is a mode 1 crack opening test where you peel two different laminates apart from each other. D5905, which is a mode 2 in plane shear test, and D6671, which is a mixed mode bending test. Of course, many of these same test configurations can be performed in terms of fatigue of composites. And then there's entire component testing, which is possible by mounting test components into a test frame, adhering strain gauges, or performing two-dimensional DIC analysis on entire pieces. In addition, there are two other very common composite constructions which are worth mentioning that have unique test standards. The first are sandwich core composites, which are composites featuring a lightweight stiff core, such as a foam or a cellular metal that's laminated between two thin, strong skins that create a lightweight stiff board material. The common test methods for these types of sandwich core composites are a beam flexure test in C393, shear properties of the sandwich with C273, and a climbing drum peel test where you measure the force to separate the skin from the core. And another category are pultruded composites, which are generally long axial composite pieces that are formed by simultaneously running fibers through an assembly line and compiling axial components, such as on the right, a composite rebar material. Tensile properties of reinforced composite bars is measured with D7205. These materials are extremely strong axially, and they generally require a very large gripping area. So it's common to perform that testing on a hydraulic test, such as the Shimadzu pictured on the right. So in the last few slides, I'll discuss some of the general instrument requirements to consider if you are going to be performing composite testing. The first is test forces. So since composites are such strong materials, many of these test forces, especially tensile tests, can exceed 100 kilonewtons. So you'll have to ensure that you have the right capacity for testing. The next is the high gripping forces required for tensile testing. It's common to perform testing with hydraulic grips in order to have the controllable gripping force, large gripping area, and high alignment. Testing with composites may also require alternative grip face surfaces such as diamond-coated grips or different serration patterns. Sample tabs may be required, but they are time-consuming and may fail due to poor adhesion, so sometimes it's really important to instead optimize the grips that you're using. Another big advantage is the ability to switch between many components and fixtures. As I showed you, the majority of the test standards I just discussed each required a different type of fixture. So if you have a setup that makes switching between tension and compression easy, that can be a huge time saver. Next is alignment. I'll go into more detail about that in the next two slides, but there are very specific requirements for alignment for many of these test standards that require a precision alignment system. And then finally, testing environments. Several of these standards can be performed at elevated or subambient temperatures, and there are different solutions for that. Shimadzu's AGXV test frame, which was released just a few years ago, was designed specifically for the demands of composites testing. It comes in capacities of 10 kilonewtons to 600 kilonewtons, and it's got a expandable input-output box for a variety of different strain measurement techniques and a few convenient options such as a smart controller and intelligent crosshead. A bit more about alignment. So as I mentioned previously, composites are very stiff and they're not ductile, which means that misalignment produces uneven stress distributions such as bending and concentrated stress that will cause premature failure because you're not applying the stresses either directly aligned with the reinforcing fibers or maybe the sample may not be mounted correctly within the grips. So there are actual requirements for performing tensile tests of certain composites that require the measurement of alignment, such as ASTM E1012 and NADCAP requirements. You can see as represented on the right, you can measure the contribution of different concentric and angular alignment of the grips and correct for that by making adjustments to the alignment of the upper and lower grips. You can do that using something called a precision alignment system, which is pictured at the bottom left of the frame. It is an additional piece of hardware that mounts between the crosshead and the load cell and grips of a test frame, and it allows you to make fine horizontal and angular and rotational adjustments to the grips. You typically mount a strain gauged reference specimen in the grips, and ideally this is going to be a specimen that's got very similar size and dimensions to the specimens you'll be testing. And then you use specialized PAS software, which is pictured on the right, to measure the contribution of strain across of the strain gauges attached to the reference specimen. So on the right, you can see that you typically have 4 strain gauges mounted on each of the 4 faces of the sample, and then at 3 different positions along the length of the sample. And you apply a tensile force to the specimen, measure the strain, and then make fine adjustments. Typically, once these adjustments are made and verified, everything, the grips and the load cell and everything must be left in place after verification so that you know that they stay in specification. This PAS system is also frequently used in fatigue testing setup as well. The other instrument requirements that I mentioned are fixtures and environmental chamber. If you are doing in-chamber testing for elevated and sub-ambient temperatures, Shimadzu offers several environmental chambers that can cover from -70 up to 280 degrees Celsius. And then the fixtures. So for our standalone test frames without environmental chambers, we offer a multi-joint, which is a system that allows you to easily switch between different fixtures and even different load cell capacities to switch between tension, bending, and compression fixtures. We also have some solutions kind of for higher forces, such as an in-chamber hydraulic system pictured on the right. This system actually also has a PAS installed, and it allows you to do tensile testing in chamber, or you can mount compression plates to the surface of the grips in order to use all of those compression and shear fixtures as well. And finally, extensometers and strain measurement. Very common question when performing composites testing is which kind of extensometer do you need? And it's really going to depend on the fixture that you're using and what you're trying to measure. Strain gauges are still required for the measurement of very low strain and in certain situations, such as in jigs with constrained access to the sample surface. So in some instances, you cannot get away from strain gauges, but they, because they are a little more time consuming to use, but they still provide some exceptional strain measurement. In line with that, the AGXV was designed with room for up to 20 simultaneous analog strain gauge sensor inputs, which is useful for either measuring several different channels of strain at once or testing entire components. Contact extensometers are a low-cost, convenient option for measuring fixed gauge length testing. So for tensile testing and Poisson's ratio contact extensometers are a very convenient choice. Automatic extensometers are also potentially convenient for high precision and high throughput tensile testing if you're performing the same test over and over again. And then finally, there are several non-contact extensometer options. Shimadzu's TRVUX non-contact extensometer is capable of performing DIC analysis, and our test frame is also capable of receiving analog inputs from different non-contact extensometer options. All right, and that's the conclusion of what I've prepared today. I hope that was a good introduction of some basics composites test standards, and I'd be happy to take any questions now.
Thank you, William, for that excellent summary of composites testing standards. I know these standards can be very difficult, and I think it was a great introduction for people who want to start testing composite materials. There have been several questions that have come in throughout the presentation, so if you're ready, we can get started with the Q&A.
Sure.
All right, the first one, it says, you mentioned that tabbed ends may be required for tensile tests. How do I know if I need tabbed ends or not?
Yeah, that's one of the most common questions. Tabs are used in tension and compression tests, actually. The purpose of tabs are to prevent premature failure due to an undesirable failure mode, such as damage to the composite from the gripping surface. That's the most common reason you need it. Tabs are strongly recommended when you're testing unidirectional materials or materials that are strongly unidirectional that will fail in the fiber direction, because those are going to be tend to be extremely strong and also still the most sensitive to the force of the grips. So tabs may also be required when testing unidirectional materials in the matrix direction to prevent gripping damage. So tabbing materials are available. The most common is a glass fiber resin with a 45-degree cross ply. You can buy those even prepared to adhere onto the material. But essentially, you try testing a material first without a tab and observe the failure mode. And if you are seeing that an undesirable failure mode, then you should try tabbing. This is also a good question and brings up a point I could have gone into a little bit more detail in relation to compression tests. There are many composite standards that have sections at the end where you inspect the test piece to identify failure mode and location, and that's commonly reported with the result. So to summarize, if a failure mode isn't right or if there's large variability, then the sample should potentially be tabbed or tested separately.
Great. So the grip faces themselves and the serrations, those can sort of damage your sample and cause some sort of a weak point or something like that with the tabbed samples.
Yep, exactly. The serrated grip faces are typically something like a diamond pattern or diagonal shape that actually digs into the surface of the composite, and that's why they're good at gripping, but that may actually cause laminate layers to be cut or damaged.
And in the case of the CLC test, the combined loading compression test, the tabs can, I guess, help distribute some of the load and improve or give you a better failure mechanism.
Yes, yeah, that's a good point. And for instance, in the CLC test or in some of the shear tests, that extra layer of material between the gripping surface and the material helps ensure that the shear forces are going to be applied without damaging the material itself at the ends.
Well, fantastic. I think that's really some valuable insight that could save a lot of people some time once they start to navigate these tests themselves. So we got another question here. It says, why do you need a mount to test single fibers? So I guess they're talking about the filament testing and the mount that you mount the fibers to.
Yeah, I mentioned that in the tension test section. There are common tests for testing individual fibers and toe. As you can imagine, it would be rather difficult to grab a single fiber and make sure that it's perfectly centered and aligned in the grips, since it's going to be flexible. And also, single fibers tend to slip out of flat grips. So it's common to create a mount that's made out of paper or cardstock or even just tape, to actually tape down the sample first in kind of a box shape, and this gives more area to grip the ends of the fiber and makes it easier to hold as you mount it. And then after you mount it, you simply cut the sides of the tape mount or the paper and to separate the top and bottom mount, and then perform the test.
Oh, I see. Yeah, individual filaments can be relatively brittle. So if you're trying to, load a filament the size of a human hair, maybe even smaller, it could be really difficult to get that into a pair of large grips.
Mm-hmm.
So the cardstock you cut an opening in there, and you mount the filament across that opening, and then in order to load it into the grips. Is that correct?
Yep. Yeah. Exactly.
Awesome. Yeah, that seems like some like a good tip that could save people, a lot of frustration.
Yeah, that's a test that requires a lot of dexterity to pull off.
Great. All right. The next question: how do I know what capacity test frame I need?
This is a very common question as well, and it's a little difficult to answer generally because it's really going to depend on the type of material you're testing. The strongest unidirectional composites under tension can just generally, with the standards I discussed, can often require over 50 kilonewtons of force. So our larger capacity test frames are often used by Composites customers. They're also compatible with some of our larger gripping options like hydraulic grips. So it's common for Composites customers to get a 100 kilonewton or 300 kilonewton test frame. But of course, the shear and bending tests are generally going to be lower in force, probably around or below 20 kilonewtons. So it's better to go with a larger test frame and have the option of going down than getting a small test frame and not being able to go up. There are a few options to cover the whole range. You can get a wide type load cell that can measure down to 1/1000th of the load cell capacity, or we have options to mount low capacity cells. As I mentioned with our multi-joint, you can mount lower capacity load cells onto the existing fixtures that you have. And again, that's a general answer. It's going to depend widely on the type of test you're doing. So as I say, it's kind of good to maybe do some rough calculations based off the standards that you're trying to follow to get an idea of test force, but then also keep in mind what other tests you might want to do in the future to choose a test frame that's going to be as versatile as possible.
I see. So, so basically it depends on the strength of your material and the size of the material, but to generalize, 100 kilonewton test frame is kind of, fits the bill for most of these applications and the standard sample sizes, and you can go up or down from there. But it's always good to think ahead about some of the testing that you would want to do in the future in order to make sure that you'll be able to use the same test frame for all of the testing that you may be not currently doing but planning to do.
Yep, exactly.
All right, the last question, got another one here. So this question is related to strain gauges, and I know this causes a lot of confusion for a lot of people. It's a lot of the composite standards recommend or require strain gauges, and there seems to be a lot of confusion around that topic. So it says, how do you connect strain gauges to your test frame?
Yeah, that's a great question. So for those that aren't too familiar with strain gauges, they're basically little pieces of foil that act as resistors, and their resistance changes as they're stretched or elongated. And you need three basic components for strain gauges. You need something called a bridge box, which is basically a connector that you connect the strain gauge to and helps complete the circuit. And then you need an amplifier that's going to actually provide the voltage to excite the strain gauge and output that signal. And then in the case of using a Shimadzu test frame, you then need an analog input card from Shimadzu to read the signal that's output from the amplifier. More specifically, our analog inputs use a conventional 0 to 10 volt analog signal. So you need to have an amplifier either from us or from the supplier of your strain gauges that can output that 0 to 10 volt analog signal. On our test frames, that analog signal goes into the test frame, and it actually goes straight into our trapezium test frame software. So you'll be able to read it as a data channel right there in the software, and you can incorporate that for use in calculations. So you can base your modulus and strain calculations off of the strain gauge signal, and you can also use it real time. You can see the signal real time, but also use it for strain control testing.
I see. So at that point, it's the strain gauge signal is the same as any sort of sensor or like extensometer that you would normally connect to a test frame?
Yeah, it'll show up just like an extensometer would in the software.
And I know with analog signals, a lot of times there's some sort of like a calibration that needs to happen to make sure that the signal is scaled properly. Do you have to do any sort of calibration with the Shimadzu test frame, or how does that work exactly?
Yeah, that's a good point. Yeah, so our software is configured so that you can calibrate the signal. So if you to scale it within the software and tell it basically what 0 and full scale reading is, it's gonna the strain gauge is gonna output. So it's kind of built into the software that when you connect the strain gauges and open it up, you perform that calibration first.
Okay, but it's I guess correlating a specific output from the amplifier to a some amount of elongation.
Exactly. Yes. Yeah.
Okay. Perfect. That's an excellent explanation for that, and sounds pretty straightforward to get strain gauges connected as long as you kind of know what it is that you're you're trying to do.
Yep.
All right. Well, it looks like that's all the time we have for today. Thank you again, William, for your time and insights. I'm sure this is very useful for a lot of people out there. Remind everybody listening, if you have not filled out our survey, please take a moment to do so. And until next time, happy testing. Thanks.